This video is on the common collector transistor and on the common drain transistor. So what we mean by common collector is that the collector terminal is not being used as an input or an output. And when we consider the base is a bad output, and it's a bad output because it doesn't output or conduct significant current. If it's a bad output and we only have one other terminal, then this terminal must be the input. In other words, if we look at the transistor right here, it's a common collector, so the collector is not being used as an input or an output. So it has no small signal variations, and we connect it to small signal ground. We know the base cannot be an output, so it has to be the input, and then the emitter therefore has to be the output of this configuration. So now the first thing we will do is replace the BJT symbol with its small signal equivalent circuit. And what we have is we have R pi connecting from the base to the emitter. We have a GM current connecting from the collector to the emitter. And then we have a little RO connecting from the collector to the emitter. The collector has no small signal variations, so we connect AC ground to it. The base is the input, and the emitter is the output. So now what we will do is we will map this out into an equivalent two-port network, which has an equivalent input resistance, a short circuit transconductance to the output, and a short circuit output resistance. So let us first figure out the input resistance. And the input resistance is just the small signal translation from the input voltage into the current into the circuit. So here when we look at the equivalent circuit, we're looking at the small signal translation from this little Vn into the current going into the base terminal. So the first thing that we note is the input voltage. Well, we see that the input voltage is basically a base emitter voltage that is stacked above the output voltage. So it's the sum of those two, and we see here the output voltage stacked with the base emitter voltage. The next thing that we'll note is the output here. We're going to connect a circuit to the output that is going to present an equivalent load resistance, and we're just going to call this RLD for the equivalent load resistance. So when we look at the output voltage, we note that that load resistance is in parallel with the output resistance, little RO, and that's because they both connect from the emitter to AC ground. And that's what we have here. So the output voltage is the ohmic translation of a current going into those two resistances. The current in this case is basically the base current plus the GM current. And that's what we see here, the base current plus the GM current into that combined resistance. Well, the GM current is the base emitter voltage into GM. But then we know that the base emitter voltage is a voltage across R pi. So it's an ohmic translation of the current going through R pi. That's the base emitter voltage, and that's what we see here. Base current into R pi gives us the base emitter voltage. So now, if we remove all the markers here, we can make an observation. First, we know that the base emitter voltage is now basically the base current into R pi. So when we look at the numerator here, we have a base emitter voltage which has a base current, and we have an output voltage whose every term also has a base current, and we'll write it over here to make it more distinct. Base current into R pi. So we can cancel all the base current components from the numerator and denominator. So we cancel this one, we divide top and bottom by that. This one disappears, this one disappears, this one disappears. So when we get the equivalent expression, what we'll have here is from the base emitter voltage term, we only have an R pi, so that appears here. Then we have 1 times the parallel combination of the load resistance and little RO, that's the second term. And then we have GMR pi times the same resistance, and that's the third term right here. And here we can make some observations before we go forward. We note that GMR pi, well, remember R pi is beta times greater than 1 over GM, so GMR pi is just beta. So this third term is beta times greater than this parallel combination, and beta is between 50 to 100. That means that that third term overwhelms the effects of the second term. So then we can conclude that the equivalent input resistance is R pi plus beta times greater than that parallel resistance, which means that the input resistance is greater than or equal to R pi. And how much greater depends on what load resistance we connect to the output. So now we have the input resistance of our two-port network. Let us look at the short circuit transconductance. In short circuit transconductance is the small signal translation from input voltage to output current when the output voltage is grounded. So we look here, first we're going to ground the output voltage, and we're looking for the small signal translation from the input voltage to the output current this way. The next thing we note, if we look at little RO here, is grounded on both sides, so the voltage across RO is 0. What that means is that the current through RO is 0, which means that RO is not having any impact on the circuit. It's as though it's not even there. That simplifies the circuit, and we can now continue our analysis. So when we look at this total output current, is the combination of two currents is basically the base current plus the GM current, and that's what we have here. We have the base current I sub B and then the GM current. But then we know that the base current is basically an ohmic translation of the voltage across R pi into R pi. And when the output voltage is grounded, the voltage across R pi is just the input voltage, because the input voltage is then connected to ground. So the base current is just an ohmic translation of that input voltage in R pi. And then the GM current, which is a function of the base emitter voltage, well, under these conditions, the base emitter voltage is the input voltage. So the GM current is also a function of the input voltage. This is very convenient because we can cancel all VN terms. And what we see here is that the equivalent short circuit transconductance is 1 over R pi plus GM. But GM is beta times greater, that current is beta times greater than 1 over R pi, so GM overwhelms the effects of R pi. So the short circuit transconductance reduces to just GM. So when we look back at our two-port network, now we've got the short circuit transconductance. All we need is now the short circuit output resistance. And let us remove markers so that we can start again here. The short circuit output resistance is basically the small signal translation from the output voltage into whatever current is going into the circuit at the output when the input voltage is grounded. So when we look at that combined current, we have three components. We have the current going into R pi, we have the GM current, and the RO current, and that's what we're noting here. Those are the three current components that we have. But the R pi current is just an ohmic translation of the output voltage. So that's what we note here on the first term. The RO current is also an ohmic translation of the output voltage, so that's what we note on the third term. The last one, if we look at the base emitter voltage under these conditions, which is basically the voltage across R pi, that base emitter voltage is also the output voltage, but in reverse. So what we have here is minus V out. But we can remove the minus and basically reverse the current in the opposite direction. And that's basically a trick that allows us to simplify the circuit. So basically, it's the current going from the emitter to the collector. So the GM current is a GM translation of the output voltage, and that's what we have here. GM translation of the output voltage. So when we look at this, again, we can cancel all the little VOs, the output voltages, and what we notice is that what we have here is 1 over the sum of the conductances. This is the same as saying as the parallel combination of equivalent resistances. And this makes sense because if we look back at the equivalent circuit, what we're looking for is the equivalent resistance when we look into little VO. That's the parallel combination of everything connected to it. So we have R pi in parallel with RO in parallel with a GM translation of the output voltage. And that's what we have here, the parallel combination of those three. But R pi is beta times greater than 1 over GM. So its effects are overwhelmed by 1 over GM. And RO is even greater, so those effects are also overwhelmed, so the output resistance reduces to pretty much 1 over GM. So let us do an example to see how this translates to numbers. Let us bias the transistor with 100 microamps. Let us connect a load of 50 kiloohms to the output. Let us use a transistor that has a current gain of 100 amps per amp and an early voltage of 50 volts. Well, first we can look at the GM, and GM is a thermal voltage translation of the bias current, and that's 3.9 millisiemens. Then we look at R pi. R pi is beta times greater than 1 over GM, and 1 over GM is 260 ohms, so R pi is 26 kiloohms. Then we have little RO, and little RO is an early voltage translation of the bias current, and that gives us 500 kiloohms. So now we can look at the short circuit transconductance, and remember that's 1 over R pi plus GM, which is roughly just GM, which is 3.9 millisiemens. Then the input resistance, well, that's R pi plus the load in parallel with little RO plus beta times greater than that load, and it turns out to be roughly 4.7 megaohms. And that kind of makes sense because it's beta times greater than the load resistance, which would be 5 megaohms. Slightly lower because of the role of little RO. And then finally, the equivalent output resistance is just 1 over GM, roughly, which is 260 ohms. So now that we have the two-port equivalent network for our circuit here with these three parameters, we can get the gain of the circuit. And the gain for that two-port model is basically the short circuit transconductance current into the combined output resistance. And we see that the combined output resistance is 260 ohms in parallel with 50 kiloohms. The 50 kiloohms has very little effect. The 260 ohms is 1 over GM. That times the transconductance current, which is GM, is roughly just 1. What that means that the voltage gain is 1. So if we put a 10 millivolt sinusoid at the base, we're going to see roughly a 10 millivolt sinusoid at the output. That means that the output follows the input. And this is why we call this a voltage follower. Sometimes we call it an emitter follower, but they both mean the same thing. Well, how about the Mosfet? We said at the beginning that we would also talk about the Mosfet. Well, the Mosfet is pretty much the same because when we look at the small signal equivalent circuit, it decomposes into very similar components. But what's different? Well, the Mosfet does not have a gate resistance. So R pi in our derivations will tend to infinity. So when we look at the equivalent circuit here, there's no gate resistance. It disappears. We still have a GM current, and we also still have a little RO. In the case of the MOSFET, we call it RDS. The other difference is that we have a GMB current here. Now, usually what we have there is VBS into GMB, and the current is going down. But the body here usually has no small signal variation, so that's equal to minus the source voltage. And the source voltage is just the output voltage. So first let's deal with the minus. We remove the minus and we can reverse the current. And that's why the current is reversed here. Second thing is that the source voltage is equal to the output voltage, so that's why then we use this output voltage here in the model. So let us remove markers here so we can see the equivalent circuit. So what we're saying here is that the GMB current is actually a GMB translation of the output voltage, which is another way of saying that we can model it with a resistance that has whose equivalent resistance is 1 over GMB, because when we look at the current through that equivalent resistance is the output voltage over that equivalent resistance that gives us the GMB translation that we had from our previous equivalent circuit. So what we're saying here is that the effect of GMB is to load the output. In other words, GMB here is basically in parallel with RDS. So if we remove all markers here, when we look at the equivalent two-port model, when we look at the original equivalent input resistance, it was R pi plus some other terms, but R pi now tends to infinity, so the input resistance will tend to infinity. Then we have the short circuit transconductance. The original was 1 over R pi plus GM, but since R pi tends to infinity, 1 over R pi tends to 0, and the short circuit transconductance reduces to just GM. If you notice here, I'm using an equal sign here instead of an approximately equal sign for the BJT, and that's because there is no R pi in the Mosfet. And lastly, the equivalent output resistance. In the original, we had R pi in parallel with 1 over GM in parallel with RO. So 1 over R pi, well, remember R pi tends to infinity. Sorry, not 1 over R pi. R pi. Well, R pi tends to infinity, so when it's in parallel with anything else, the effects of R pi then disappear. That's why there's no R pi here. Then we have little RO, which in the Mosfet is just RDS. We have the 1 over GM component. And lastly, we have the effect of GMB, which remember we said the effect of GMB is to load the output with an equivalent resistance of 1 over GMB. So this is how it appears here. Basically, the Mosfet behaves just like the BJT, and we call it a source follower, or more generally a voltage follower. And if you look at the gain here, the short circuit transconductance gain into the equivalent output resistance, we still get the gain of roughly 1, which is why we call it a follower. Well, I hope this was helpful. Thanks for watching.